Okay, we are going to talk about buffer solutions. Okay, now what is a buffer solution? It's important this word here, resists. It resists changes, A and pH, after addition of small amounts of acid or alkali or water to a solution. It doesn't not change at all, it resists it. Okay, so it's very important in biochemistry or biology experiments. You know, if you've got an enzyme in there, enzymes are very sensitive to pH. If you change the pH, they'll stop working. So the solution needs to be buffered so that the pH remains at the required level all the time. Buffers are also found like in swimming pools to keep the pH of the water constant. If people wee in it, it makes it go very alkaline. They're found in foods. It's usually, if you look, it's called an acidity regulator. If you look on the back of like tomato ketchup or something, they've got buffers in them as well. Right, now what is a buffer solution? Right, a buffer solution is made from a weak acid. It's a mixture of solution, a weak acid and its conjugate base. So in other words, it's going to be HA and A minus. Of course, you can't get a bottle of A minus. You need to have, it comes with a positive ion, so it's usually the sodium salt. So some people might say it's a weak acid and it's a mixture of weak acid and its salt, okay? Which is the same thing as saying it's conjugate base. Okay, so you need lots of HA and you need lots of A minus for a solution to be a good buffer. So that's why if you just had say if you had some ethanoic acid, it wouldn't be a buffer, a very good buffer. You've got this equilibrium going on, haven't you? But how much A minus have we got? Well, we've got hardly any because it is a weak acid. So let's try and talk about how a buffer actually works qualitatively, and then we'll get on to doing some calculations of the pH. This is mostly just qualitative discussion here. Right, so here is our buffer solution here. And as you can see, I've drawn lots of A minuses and lots of HAs all floating around in solution. Right, now we have got this, we've got a couple of equilibrium going on there, haven't we? We have got HA goes to A minus and to H plus. And we've also got the KW equilibrium. So we've got H2O dissociating. Okay. Right, we've got equilibrium 1 and equilibrium 2. Right, so let's say we add a little bit of acid. Okay, so we resist changes after a small amount of acid. Okay, so we're going to add a little bit of acid there, some HCl or something. What will happen? So we add acid. Le Chatelier tells us, if you add acid, what will it do to this equilibrium? So equilibrium 1. Equilibrium 1 will move to the left. And so that means the concentration of H plus ions will not increase very much. In order for this to move to the left, you need make sure you need plenty of A minus. So that's why you need lots of A minus. So if you add a bit of acid, it will just kind of like the A minus reacts with the H plus and mops it up and stops the concentration of H plus getting too high. Let's see what would happen if you added some alkali. So add some OH minus. That's a bit more difficult because if you add OH minus, what will it do to equilibrium 2? It will move that to the left, yeah? What will that do? That will effectively lower H plus concentration. Well, and that will then have an effect on equilibrium 1. If you lower H plus concentration, that will make equilibrium 1 try and raise it by moving to the right. Okay, and it will make some more H plus. Now what do you need in order for that? Sorry, not A minus, it will make some more H plus. What do you need in order for that to happen? Well, you need to have plenty of HA. So that's why you need the HA to push it that way. Okay, so that is the qualitative discussion of it. Now, whenever you, just before we finish, whenever you're doing a buffer calculation, it's a good idea to rearrange your Ka expression. So what's Ka equal to? It's H plus conc A minus over HA. So I'm going to rearrange to make H plus the subject of that equation. So H plus concentration, which of course is going to give us pH, is going to be equal to Ka multiplied by HA over A minus. So this is going to give us pH. So we can see the pH of a buffer solution is dependent on two things. Right, it's dependent on Ka of the weak acid, which of course doesn't change. And the other thing it's dependent on is this, which is the ratio of the concentration of the weak acid to its conjugate base. Okay, so you can change the pH of a buffer by changing this ratio a little bit. And that's, if you ever want to work out the pH of a buffer solution, that's what you're going to have to put the equation in this form, and that's your starting point. So let's leave that there. We'll do calculations in the next video.